Hello, Bacho. Welcome. Today we're going to tackle a really interesting topic from our Unit 11, the wave nature of matter. Now, I know this idea can seem a bit strange at first, but trust me, by the end of this session, we'll make it so simple that it becomes one of your favorite topics for the exam. तो चलो, शुरू करते हैं.
Alright, so just think about this for a second. One of the most beautiful things about physics is that it shows us how balanced the universe is. Nature just loves symmetry. We just learned that light, which we always thought of as a wave, can also act like a particle, a photon. And that discovery makes a very simple but very powerful question pop into our heads. If a wave can pretend to be a particle, then for nature to be perfectly balanced, shouldn't a particle also be able to act like a wave? It just makes sense, right? It feels like something is missing otherwise. This one question, Bacho, is the key to this entire chapter. And the person who was brave enough to ask this question and then answer it was a young physicist from France, Louis de Broglie. Back in 1924, he came up with an idea, a hypothesis, that was so bold, so different, that it completely changed how we see the world.
You know, the amazing thing is how simple his thinking was. De Broglie didn't start with some complicated maths or experiments. His idea came from a deep belief that the universe is elegant and symmetrical. He just said, look, if light has a dual nature, then to keep things symmetrical, matter must also have a dual nature. It was just a beautifully simple idea.
So, how can something be a particle and a wave at the same time? It's a bit confusing, Hina. Let's use a very simple analogy. Think of a coin. It has two sides, right? Heads and tails. But you can only see one side at a time. The coin is always a coin, with both sides. An electron is just like that. It's always an electron, with both a particle nature and a wave nature. It doesn't change from one to the other. The type of experiment you do simply decides which face, which nature you get to see.
Okay, so an idea about symmetry is nice, but this is physics. We need math to make it real. De Broglie didn't just stop with the idea. He gave us a formula to actually calculate the wavelength of these so-called matter waves. And beta, this formula is extremely important for your numericals, so please pay close attention. Now look closely at this beautiful formula. On the left side, we have lambda. Lambda, that's wavelength, a pure property of a wave. On the right side, we have momentum, p, which is mass times velocity, a classic property of a particle. And what's connecting these two totally different worlds? That magical little h, Planck's constant. It's like a quantum bridge that connects the particle world and the wave world. Now here is the most mind-blowing part. This formula isn't just for tiny electrons. No, it applies to every single moving object. You, me, this pen, a cricket ball, anything that has momentum also has a de Broglie wavelength. Just let that sink in. Every moving thing is also a wave.
I know what you're thinking. Sir, if a cricket ball has a wave, why don't we see it bending around the batsman? Excellent question. And to answer that, we need to do a little bit of calculation. Let's find out just how big this wavelength is for a particle we all know, an electron. The calculation is a very simple three-step process. Dekho. First, we just find the momentum. That's just mass into velocity. Easy. Second, we put that momentum into our de Broglie formula. And third, we just look at the number we get. Simple enough, right? Take care. Chalo, let's do it.
Okay, so here are the numbers we need. We'll take the standard mass of an electron, which is obviously very small. Let's say it's moving pretty fast. That gives us its momentum. And of course, we have our special connector, Planck's constant. These are all standard values you'll find in your exams. Now, when we plug these values into our lambda equals h by p formula, we get this number, 0.73 nanometers. That is unbelievably small. It's 0.73 into 10 to the power of -9 meters. Tiny. But wait, here comes the magic. That tiny number, 0.73 nanometers, might seem useless, but it's actually about the same size as the gap between atoms in a crystal. And because the electron's wavelength is similar to the size of the gaps it's passing through, it can actually show diffraction and interference, just like a light wave. This is not just a theory, it's been proven in experiments. Now, Bacho, let's talk about the important part for your exams. This topic has a few silent killers. These are common misunderstandings that can make you lose marks. Let's expose them so you don't fall into these traps.
So, the biggest mistake students make is they think a particle changes into a wave. No, that's wrong. Remember the coin.
the electron always has both natures. And the wave isn't some physical thing running behind the electron. You should think of it more like a probability wave. It's a wave that just tells you the chances of finding the electron at a particular place. Where the wave is strong, the probability is high. Simple.
And this brings us back to our favorite cricket ball question. This is the most common doubt everyone has. If the ball has a wavelength, why doesn't it behave like a wave? Why doesn't it diffract around the wicket?
And here is the answer. If you actually do the math and calculate the de Broglie wavelength for a cricket ball, you get a number around 10 to the power of minus 34 meters. I mean, we can't even imagine how small that is. It's trillions and trillions of times smaller than one proton. And remember the rule, to see wave effects, the wavelength must be similar in size to the obstacle. For a cricket ball's wave, there is no obstacle in the universe that is small enough. So yes, the wave nature is there, but for big objects in our world, it is completely, totally negligible.
So you see, with de Broglie's fantastic idea, the picture is finally complete. That beautiful symmetry of nature is restored. It's not just waves that can act like particles, it's also particles that can act like waves. This wave-particle duality is a fundamental rule of our universe.
And why should you care? Well, this isn't just some abstract idea. The wave nature of the electron is the actual reason that atoms are stable. In the next chapter on atoms, you'll learn that electrons don't circle the nucleus like little planets. No, they exist as stable standing waves. Only certain wavelengths can fit perfectly in an orbit, and that is why electrons have specific, fixed energy levels. Without this wave nature, every atom in you, me, and the entire universe would just collapse.
Okay, so let's do a quick summary for your exam. What are the key points to remember? First, the formula. Every moving particle has a wavelength. Lambda equals h by p. Second, this completes the symmetry. Both matter and radiation have a dual nature. Third, this wave nature is only significant for tiny, microscopic particles like electrons. For big, everyday objects, it's negligible. And finally, the hero who connects the two worlds is Planck's constant, h. Got it? Simple.
And I'll leave you with one final thought to think about. If every single moving object has a wavelength, and you are an object, and you definitely move, does that mean that right now, as you're walking around, you have your own personal wavelength? Think about it. That's the amazing, strange world of quantum physics. Keep studying, and I will see you in the next one.